This screencast is a brief introduction to small world graph models done from my network science class. It assumes that you've already read about them, and it will give a brief introduction to some of the properties of small world models in igraph and R, and then we will try to model a graph with a small world model. First, we'll review how the Watts-Strogatz model works, and then we're going to look at the clustering distance trade-off. Okay, I'm going to go through this fairly quickly because you should have already reviewed this. We make a small world with sample small world. This is the number of dimensions. This is the number of vertices in each dimension, the number of neighbors, and the probability of rewiring. This is the example from sand. Just a quick visualization to remind ourselves that a small world is a lattice that has been rewired with some probability. So the lattice part is the connection to the 5 neighbors that you see around there, and then the rewirings tend to cross that. And it has high transitivity, and it has short distance. So we can see, looking at the setting ourselves up for the trade-off here. Here I'm going to make a small world model of 1 dimension and 100 vertices, 5 neighbors, but no rewiring. And I'm going to graph that and compare it to one with rewiring. So let's give it 2 columns in the graph and plot it. And now here you see the links to the neighbors being drawn in, and there won't be any crossings because we have specified 0 probability of rewiring, and that of course gives us very high transitivity down here and high distances for this graph. Okay, got 10 and 5.5. Now the same thing, but let's just rewire 5% of the edges. Okay, and so let's plot that one. So you see the crossing edges coming in here along with some of the close neighbor edges, and it looks like that. And now let's compare. The transitivity for this one has dropped from 0.6 to about 0.4, while the distances have gotten a lot shorter, a diameter of 5 instead of 10. We've cut the distances in half with just a rewiring of 0.05. So noticing that the unrewired graph has high transitivity and high distances, and the modified one still has moderately high transitivity and shorter distances, we wonder how much do we have to rewire to get the distances while preserving transitivity. So this leads to the question of what the trade-off is, and that's what we're going to study here. So what we're going to do is a little program here. We're going to make some powers of 10 with seek that says start at -4, go up to minus 0.5 in steps of 0.1. So here's a bunch of numbers in a sequence, and there are 36 of them. So we're testing 36 possible powers of 10. These powers of 10 will give us the probabilities from very low probability of rewiring to fairly high probability. Okay, so here's we're going to make a list of 13 zeros, which is where we're going to accumulate the clustering results from each of these 13 powers. We're going to run trials for each of the 13, and the same for path length. PL is path length or distance. And here we're going to run only 10 trials just for time's sake. 100 might be better. Okay, so here's the code. I'll explain it briefly. We're going to run a loop and an inner loop. The outer loop will be for the 36 powers of 10. We're going to print something out just to let us know it's running, and we're going to make temporary versions of these results vectors here, in which we restore the clustering and path length for this power of 10. We're going to run the n trials, which is 10 trials. So here's the call as a sample world. We're going to run 1,000 vertices with 10 neighbors, and we'll get the power of 10 out of here. And then when we get these 10 trials, we're going to take their average, and first we're going to store them in here. And when we get out of the loop, we're going to take their average and store them in the results to get the mean value for those 10 trials. And again, 100 would be better, but just to make it quick, so there it goes. It's running through, printing out each outer loop for different powers of 10. And now it's done. Okay, so now we're going to plot the results. So we're going to make a window here for the results, and this is straight out of the SAM book with some minor modifications, and there's your result. This shows that we only have to do a very small amount of rewiring to greatly reduce the distance. In fact, we can reduce the distance a fair amount without hardly touching transitivity at all. Right here is like the sweet spot where you get almost the original transitivity but much shorter distances. And then as you do too much rewiring, it gets more like a random graph, and then the clustering coefficient or transitivity plummets. So this is the original graph that they had in the Watts-Strogatz paper, Nature 1998. It's a version of similar to what they had, showing this trade-off. Now let's move on to modeling a graph with a small world. So we're back in R, and I've already loaded in this graph, the yeast graph, which you can get from the SAND data set or load from your directory, as I did in the previous video on random graph modeling. So we're continuing from the previous video here. When we model a small world, we want to know how many vertices are, because we want to match that and try to approximate the number of edges. So here I'm going to tell it I want one dimension, a circular lattice, with the number of the vertices required, and I'm going to take a guess that if I put in 4 neighbors, I'll get the right number of edges, and we'll just take the 0.05 rewiring parameter. By the way, this wiring parameter, you can adjust it once you get the number of vertices correct. Then you can adjust it to try to get the right trade-off between transitivity and distance, as we showed in this graph here. I'm not going to actually do that in today's demo, but just remember that once you get the vertices and edges right, you can then start to play with this to tune it with this trade-off here to hit something that matches the actual graph you're modeling. So let's go ahead and make that and look at the graph. So we had the correct number of vertices, and we're within 1,000 of the number of edges. I've actually tried 3 and 5 here, and it gets a little bit further away, so I'm going to go ahead and go with this particular Watts-Strogatz random graph. Okay, so the whole point here was the model transitivity, so let's compare what we got to, here's the transitivity of the original data, 0.46. Here's the transitivity of the best thing we got in the random graph models in the previous video, which was 10 times too small, and here's the one we just did, which is much, much closer to the natural graph, so that's pretty good. You can actually increase transitivity, again, by this trade-off chart here, by decreasing the model probability. You know, if I was really concerned about getting that 0.01, I could maybe make this probability a little bit smaller to slide more to the left on the graph. Now let's see, similar with the average of the local clustering coefficient, we had a 0.38, and the rewired was again about 10 times too small, and this graph is a little high on that. I tend to prefer the global metric, but again, if you wanted to reduce this, the way you would reduce this is you might increase the wiring parameter, but then that would adjust the distances. Let's take a look at the distances as well. The original had diameter 15, the yeast rewired we had 8, and this small world one has a diameter of 9, so it's actually shorter than the original graph. For the diameter, mean distance is probably more important. We had 5, the rewiring had 3.5, and our current model is actually pretty close. So this is a fairly good model. Again, if I wanted to reduce the probability slightly, actually if I increased the probability of rewiring, I could tweak that distance down, but then that would drop the transitivity a bit, and so that's the trade-off there. But this doesn't match so much in other ways. The original graph had components, and this one is almost always connected. It would be very small probability that some node through the rewiring would become disconnected. And also, let's look at the degree distributions. So here we have, we'll make 2 columns. Here's the original graph, and here is the small world graph. So, you know, the power law and something crazy, it's got this sort of normal, well, actually what's going on here is, you know, most of them have very similar degree because it was a very regular lattice, so that's why you have this very peaky distribution at one particular point. I've written it out in GraphML using this command already, and I've already read it into Gephi, so we'll take a look in Gephi here. Again, from the previous video, I showed that this is the a visualization of the original graph, where given the nodes the attribute for color for the class of protein that they're in, which is, and the node size is the degree of the vertices. And with the small world, we get something really bizarrely different. Because it was a circular lattice, we had 1,000 nodes wired mainly to their neighbors. And remember, you got that circular structure, but we've disrupted it by making cross edges. So when Gephi lays it out with Force Atlas 2, it doesn't draw it as a circle. I've tried drawing it as a circle, and it doesn't really make much sense here. I think I've already done degree. Yeah, node size is already adjusted to degree. So you see here the very small variation in degree distribution, which we saw in this. Most of them have the same degree as compared to the more distributed in the yeast network. Okay, that's the end of our quick introduction to small world models, Watts-Strogatz small world models, and how to match it to a graph.